Jordan normalization is all about transforming a n times n matrix A in a very easy form. So when talking about transformation, we mean the process of finding an invertible transformation matrix X so that x to the power of -1 times A times X is equal to some matrix J. And we want to find this matrix X in a way that the resulting matrix J has a very simple form and structure. Jordan normalization is now a process to find such matrices X and J. The matrix J that has a simple structure is then called the Jordan normal form of the matrix A. This matrix is an almost diagonal matrix. This video is not about finding the matrix X. This can be a little bit tricky sometimes. It's about finding the Jordan normal form J of the matrix A. In most cases, especially for smaller matrices A, it's pretty easy to write down this matrix J. And the best thing is, you don't even have to calculate the transformation matrix X at all. First of all, we need some basic concepts. We need to find all the eigenvalues of the matrix A. Lambda is called an eigenvalue of the matrix A if and only if lambda is a zero of this polynomial here, P(ax), which is equal to the determinant of A minus x times In, where In is the n times n identity matrix. This polynomial here is called the characteristic polynomial of the matrix A. If you have problems finding the eigenvalues, there are plenty of sources that explain to you how to find them. For example, I have 2 videos on my channel that teach you how to find the eigenvalues of small matrices faster. Then we need 2 other numbers. First, the algebraic multiplicity A lambda of the eigenvalue lambda. It is the multiplicity of lambda as a zero of the characteristic polynomial. Or in other words, how often the eigenvalue occurs as a zero in the polynomial Pa. The second number we need is the geometric multiplicity G lambda of an eigenvalue lambda. It is defined as follows. G lambda is equal to the dimension of the kernel of A lambda, which is equal to n minus the rank of A lambda, where A lambda is the following matrix: A minus lambda times In, and In is the n times n identity matrix. Or in other words, the geometric multiplicity G lambda of an eigenvalue lambda is the maximum number of linear independent eigenvectors there are for the eigenvalue lambda. Okay, one last thing I want to note. Jordan normalization only works when there are exactly n eigenvalues where the multiplicity of these eigenvalues is taken into account. So these eigenvalues don't need to be pairwise distinct. Now we can take a look at the structure of the Jordan normal form J. As I said before, it's an almost diagonal matrix. Here on the diagonal of the Jordan normal form J, we have the larger Jordan blocks K lambda I. Each of these larger blocks K lambda I is an A lambda I times A lambda I matrix and has lambda I written on its diagonal. So you could say the length of one of these larger blocks K lambda I is equal to the algebraic multiplicity of the eigenvalue lambda I. Now let's take a look at the structure of one of these larger Jordan blocks K lambda I. Each of the larger Jordan blocks K lambda I is decomposed into smaller Jordan subblocks of some length L, J, I larger or equal 1. And we don't know the length of these Jordan subblocks yet. Okay, I will repeat it one more time. So on the diagonal of the Jordan normal form J, we have these larger Jordan blocks here that are of length A lambda I, which is the algebraic multiplicity of the eigenvalue lambda I. Each of these larger Jordan blocks is itself decomposed into smaller Jordan subblocks of some length L, J, I we don't know yet. And everything that is left empty here is just 0. So every empty entry here is just equal 0. Now there are two important things. First of all, we know the number of these smaller Jordan subblocks inside of one of the bigger Jordan blocks k lambda I. This number is given by the geometric multiplicity gi of the eigenvalue lambda I. So the number of these subblocks inside of the larger blocks k lambda I is given by the geometric multiplicity gi of the eigenvalue lambda I. The second thing is that these smaller subblocks inside of the larger blocks k lambda I are arranged in a descending order when it comes to their length or size. So these blocks are arranged in a descending order when it comes to the length. So the first length, the length of the first block, is larger or equal the length of the second block, and so on. Finally, we also know how these smaller blocks have to look like. They have lambda I on the main diagonal and 1 on this diagonal here. All other entries that are left empty here are just equal 0. Okay, I've written the two important notes down again. So the first thing is that the number of subblocks in one of the larger blocks k lambda I is given by the geometric multiplicity gi of the eigenvalue lambda I, which you can also see here. And the second important thing is that the subblocks are arranged in a descending order inside of the larger blocks k lambda I when it comes to their length, which you can also see here. The first length is larger or equal to the second length, and so on. So the goal now is that we want to find each length of these blocks here. So the length of the first block, the second block, and the last block. If we know the length or the size of each of these subblocks, we can write down the Jordan normal form immediately because we know how the smaller blocks have to look like. So the only thing we have to find out is the length of these subblocks here. When we know them, we can write down the Jordan normal form J. Because the number of smaller subblocks inside of the larger block k lambda I is given by the geometric multiplicity gi of the eigenvalue lambda I, and the subblocks are arranged in a descending order in k lambda I when it comes to the length, we get the following result. For small blocks k lambda I, which means that the length or the size of these blocks is smaller than 4, which means that the algebraic multiplicity of the eigenvalue lambda I is smaller than 4, we can immediately write down k lambda I only by knowing the geometric multiplicity gi of the eigenvalue lambda I. This is especially true for 2 times 2 and 3 times 3 matrices A, because these matrices can only have Jordan blocks k lambda I of length smaller or equal 3. So that means If A is a 2 times 2 or 3 times 3 matrix, and we already know the geometric multiplicity Gi of each eigenvalue lambda I, we can immediately write down the Jordan normal form J without any extra calculations. So, in case of a Jordan block of size 2 or length 2, this has to look like this here. So when k lambda I is of size 2 or length 2, which means that the algebraic multiplicity of lambda I is equal to 2, we have two options. The first option is that the geometric multiplicity of the eigenvalue is 1. In this case, there is one subblock inside of the larger Jordan block k lambda I. And the block has to look like this here. Lambda I on the diagonal and 1 here, because there is only one subblock inside of the block, because the geometric multiplicity is equal to 1. The other option is that the geometric multiplicity of the eigenvalue is 2, which means there are two subblocks inside of the larger Jordan block k lambda I, which you can see here. So the block looks like this. Lambda I on the diagonal and all the other entries are 0. In case of a Jordan block of size 3 or length 3, it looks like this here. So when k lambda I is of size 3, which means that the eigenvalue lambda I has algebraic multiplicity 3, we have three options. The first option is that Gi, so the geometric multiplicity, is equal to 1. In this case, there is only one subblock inside of the Jordan block k lambda I, and the Jordan block k lambda I looks like this. We have lambda I on the diagonal and 1 here, because there is only one subblock inside of the block, because Gi is equal to 1. The second option is that Gi is equal to 2, which means that there are two subblocks inside of the Jordan block. In this case, we use the rule that the subblocks are arranged in a descending order when it comes to their lengths. So the first block has to be the block of length 2, and the second block is the block of length 1, because they are arranged in a descending order. And so the Jordan block looks like this. Lambda I on the diagonal, 1 here, and all the other entries are 0. The last option is that the geometric multiplicity is equal to 3, which means there are 3 subblocks inside of the block, which you can see here. First block, second block, third block. So the block looks like this, lambda I on the diagonal, and all other entries are 0. Now let's take a look at some examples. The first example is the following. We have given a 3 times 3 matrix A, and the first thing we have to do is to calculate the eigenvalues of this matrix A. Because the matrix A has 0 at these points here, this is pretty easy, because the eigenvalues are in this case just the values here on the diagonal. So the first eigenvalue is 1. And this eigenvalue has algebraic multiplicity 2, because we have it 2 times on the diagonal. The second eigenvalue is 2. This eigenvalue has algebraic multiplicity 1. Because the algebraic multiplicity is equal to 1, it immediately follows that the geometric multiplicity of lambda 2 is also 1. This is a result from linear algebra. For the geometric multiplicity of the first eigenvalue lambda 1 is equal 1, we have to find the rank of the matrix A lambda 1. To calculate the matrix A lambda 1, we have to subtract the eigenvalue lambda 1 is equal to 1 from the diagonal of the matrix A. So 1 minus 1 is 0, 2 minus 1 is 1, and 1 minus 1 is 0. In the end, we get this matrix here. This matrix has rank 1. Therefore, the geometric multiplicity of lambda 1 is 2. Now we can immediately write down the Jordan normal form J. So we have two Jordan blocks in this Jordan normal form. The first Jordan block is of length 2 because the algebraic multiplicity of A lambda 1 is 2. The second Jordan block is of length 1 because the algebraic multiplicity of A lambda 2 is equal to 1. The first Jordan block looks like this here because the geometric multiplicity of lambda 1 is 2. So there are two sub-blocks inside of the green Jordan block. So the first block has to look like this here. The second block looks like this here because, well, the Jordan block is of length 1 and there is one sub-block inside of it. So it can only look like this here. And we have found the Jordan normal form of this matrix A here. Let's take a look at the second example. So I have only changed this entry here. So in the first example it was a 2. Here in our new example it is a 3 now. So the first eigenvalue is the same as before. Lambda 1 is equal to 1 and it's still 2 times on the diagonal. So the algebraic multiplicity is 2. The second eigenvalue changes. It's 3 now. And the algebraic multiplicity is still 1. And also the geometric multiplicity is also 1. Now we want to find the geometric multiplicity of the first eigenvalue. So we have to calculate the matrix A lambda 1 again. And to do this we have to subtract 1 from the diagonal of A. So 1 minus 1 is 0, 3 minus 1 is 2 now, and 1 minus 1 is 0. This matrix now has rank 2. Therefore, the geometric multiplicity of the first eigenvalue is 1. Now, the Jordan normal form changes a bit. So we have still these two green Jordan blocks here. The first one of length 2, because the algebraic multiplicity of the first eigenvalue is 2, and the second one of length 1. But now we only have one sub-block inside of the green Jordan block. So the first block looks like this. So green is the block, we have one sub-block inside, and this one looks like this, 1, 1, and 1 here. The second block doesn't change a lot. It has, well, length 1 and one sub-block inside of it. Only we have 3 here now. And we have found the Jordan normal form J. Let's take a look at one last example. So in this example here, I have changed this value here again. So here we have 3 and I have changed it into 1. In this case, we only have one eigenvalue, which is equal to 1. And this eigenvalue has algebraic multiplicity 3, because it is 3 times on this diagonal here. To find the geometric multiplicity of the eigenvalue lambda 1 is equal to 1, we have to calculate the matrix A lambda 1 again. So we have to subtract 1 from the diagonal here. So 1 minus 1 is 0, 1 minus 1 is 0, and 1 minus 1 is 0. This matrix here is of rank 2. Therefore, the geometric multiplicity of lambda 1 is equal to 1. So we can immediately write down the Jordan normal form now. So we have one green Jordan block here of length 3, because the algebraic multiplicity of lambda 1 is 3, and inside of this green Jordan block is one Jordan subblock, because the geometric multiplicity of lambda 1 is 1. So the Jordan normal form looks like this here. Let's summarize the results again for 3 times 3 and smaller matrices A. So the first thing you always have to do to find the Jordan normal form is to calculate the eigenvalues of the matrix A. When you have found these eigenvalues, you have to try to find the algebraic and geometric multiplicity of each of the eigenvalues. After that, you can immediately write down the Jordan normal form J of A by using the geometric multiplicity and the algebraic multiplicity of the eigenvalues. So the algebraic multiplicity is the length of the Jordan blocks, and the geometric multiplicity tells you the number of subblocks inside of the blocks. This is enough to tell you how the Jordan normal form J looks like. Maybe I will make another video about the Jordan normal form, where I will tell you how you can find the Jordan normal form of 4 times 4 matrices with a Jordan block of length 4. There is only one interesting special case where you need one extra condition to write down the Jordan normal form. Also, there is an approach to find the structure of Jordan blocks from length 4 to 6. And there is also a general formula for any Jordan blocks of any length. Okay, thank you for your attention, and I hope this video was helpful. Please consider subscribing to my channel if you liked this video.